Okay, so yeah, please take it away, Sylvia.
Okay, let me. All right. Hello, everybody. I thought I'd talk a little bit about the relationship of these two different approaches to safety filtering and safe control, because I believe that Professor Long is going to be talking or has talked at least about each of them, and she herself has really interesting research in each of these domains and at the intersection. And so I thought it would be a good topic to share. So the basic idea is pretty straightforward. It's that we want to have these functions that take in the desired safety constraint for your system and the long-term effect of your dynamics. So understanding that, and so encoding these long-term effects of the dynamics into the actual structure of the function. And you end up with a single scalar function for which you can query a particular state. And the level of that function at that state will be a measure of safety here. So if it's positive, it's safe. If it's negative, it's unsafe. And the gradient of that function will point you in this unsafe or safe direction to guide the control that you should use. And so these functions, there are a couple different approaches for doing them. And I'm going to introduce initially two different approaches and the relationship between them. And please feel free to ask questions during this. Let me see if I can pull up your faces so I can maybe see hands.
Yeah, I can also interrupt if someone.
Okay, all right, wonderful. Yes, please interrupt. It's meant to be like educational. Okay, first let's talk about how we would construct one of these safe functions using Hamilton-Jacobi reachability analysis. So here we take a dynamical system. We assume in this case that we have a model of the system, and that model depends on the state of your system, your control input, and potentially some disturbances that might be acting on your system, either an actual adversary that you're playing against, or just general disturbances that you need to be robust to. And then let's say that you have a region out here that is the failure region, and inside is then the constraint set, and you want to stay inside this constraint set. Well, how we would build this up is by first defining a reward function, where the reward function is simply positive if you're inside the constraint set and negative if you're outside of it. And so very, very clear here. Here we have a signed distance function to the boundary of this constraint set. And next, we want to use this to build up a value function, where the value function here, let's start with just saying we're going to tuck an initial state and time and ask what will be the reward at the end of my trajectory from this initial state and time. So find the cost, or in this case, reward of trajectories of the system starting from state X and time T. Here I'm adding in the actual trajectory notation. It can be kind of intimidating, but it's simply saying starting at state X and time T, applying some control signal and disturbance signal. This will output the state that you get to at time tau. Now we don't necessarily have to look at every possible control and disturbance signal emanating from your initial condition. It's sufficient to look at the optimal control and disturbance. Because if you can't reach your goal under your best effort, then you certainly can't reach it under less than your best effort. And so here, let's think about maximizing over the control, trying to maximize your reward, and the disturbance trying to do the opposite. And then let's encode an update equation for how we will actually solve for this. Now, this is generally some non-convex problem where you have this max min and these have bounds. It's generally very, very hard to solve this analytically. And so what we do is we discretize the state space and form a grid. And then we perform what is essentially a Bellman backup at each point, if you're familiar with that. This is just the continuous time, continuous version of doing dynamic programming, where we say if we fix a particular point in space and look at a particular X, the change in value backwards in time as we propagate backwards along the time horizon will be proportional to this Hamiltonian, where this Hamiltonian is simply saying that the control is trying to do gradient ascent. It's trying to move up the gradients of the value function to get to higher reward, but it can't necessarily move directly in the direction of higher reward. So imagine that you have a car and your reward is to the right of you, directly to the right of you. You cannot move your car to the right without having to turn it. And so since you have to obey the dynamics of your car, we look at the inner product between the gradient that's trying to do gradient ascent and the flow field of your dynamics and try to maximize along that. You assume that the disturbance is doing the opposite. And you ask, given the constraints on my dynamics and the constraints on my control input, how well do I do at trying to move up this value function? And based on that, you update your value backwards in time. This is what this looks like when we actually apply this. So now I'm doing this dynamic programming backwards in time for a time horizon of 1 second. Now, everywhere where this value is negative are states and time states from which within 1 second you cannot reach your constraint set. Everywhere where this is positive are states from which you can reach your constraint set. This is because it indicates states for which at the end of the time horizon, you will have a positive reward. So if we just slice this at 0, we can look at all of the states that will be in your constraint set in exactly 1 second. Now, you might point out to me that you don't care about being in your constraint set at the end of 1 second. You care about being in your constraint set the entire time. So how can we modify this in order to encode that it needs to be safe the entire time? Well, for this, we need to make this one step more complicated. So instead of saying that you just want to encode the reward at the end of the trajectory, we're instead going to have this min over time, where I want to encode the minimum reward that I am able to achieve over the time horizon. If that minimum reward is ever negative, then I know that I have left the constraint set. If that minimum reward is always positive, then I know that I've always stayed inside the constraint set. Now we've added a minimization to our value function here. We likewise have to add a minimization down here over time. I'm going to move this to the right-hand side and throw in a minimization. It's not directly intuitive why this min does a min over time. I'm not going to get into that right now, so just believe me, happy to get into it offline if people are interested. But this encodes that min over time. So let's go ahead and update things everywhere using this new variational inequality now. And now everything that is positive here in green, these are states from which you will always have a positive reward over your time horizon. Therefore, if I now slice this at 0, these are the states that will be in the constraint set for the entire time horizon under your optimal control and under worst case disturbance. In this case, this is for 1 second. Now, the last modification I'm going to make is, what if we care about the states from which we can be in the constraint set forever instead of just for 1 second? And for this, we continue to run our dynamic programming until it has converged. If there does exist a set from which you can stay safe forever, then we'll find it. If there doesn't, then this will vanish over time. So in this case, this converges somewhere around 4.5 seconds. And now these are the states that will be in the constraint set for the entire time horizon. We call this the control invariant set. Online, the way that we get that optimal control in order to stay inside the set under worst case disturbances is we look at the gradient of this function, and we say that the optimal control is going to be one that, again, does gradient ascent subject to our flow field, where we assume that the disturbance is going to play its worst case disturbance. This, for control affine systems, is simply an LP, and a linear program. And so it's very, very fast to solve online. The main challenge is in storing this grid and querying this gradient. You essentially do finite differencing. So properties of the, first, are there questions? Okay. So let's talk about what you get out of this function. We've now constructed this function offline. How do you use this online? Well, again, you apply the optimal control. If we look at what the optimal control is getting you, if we look back at that very scary looking update equation that we use, our version of the Bellman backup, we have 2 arguments and we say the min between these 2 arguments is 0. That means each argument must be greater than or equal to 0. So if I take this one, I say this must be greater than or equal to 0. If I plug in my optimal policy for the control and disturbance here, this is the total derivative of my value function, how it changes with respect to time, and then how it changes with respect to space, and then how that changes with respect to time. Oop, I'm missing a partial here. So I'm saying that my change in value, my change in the safety level, must be greater or equal to 0 for all time under my optimal control. This means I must never decrease my safety level. The optimal control will ensure that I always maintain or increase it. This sounds great, but this actually can be kind of annoying. This means that you must always be, if you start at a particular safety level that's high, you must always be monotonically increasing it. You can never decrease or go closer to the boundary of safety. So often what we do instead is something called least restrictive control, where instead we arbitrarily set this threshold to 0 because we want to stay positive. And when you are above 0, you can do whatever you want. But as you approach the boundary, we apply that optimal control and push you back in. And so we only apply the optimal control from the reachability in a least restrictive manner, only when absolutely necessary to keep you safe. This also sounds very appealing. Least restrictive, for the most part, you can do whatever you want while you're inside of the safety function. The main challenge is that you can find yourself bouncing off of the boundary often as you're doing this hard switch back and forth between your performance control and your safety control. And so you can end up with some, weird jerky behavior. Okay, so to recap, reachability analysis is beautiful and wonderful. You get its constructive method for how to generate these functions. It's very general. You can handle pretty general nonlinear systems with bounded control and disturbance, and it recovers this maximal safe set. You can also deal with bounded control and disturbances, as I mentioned. And I haven't gone into it, but there are many flavors beyond just solving for infinite time safety. So you can solve for reaching a goal while avoiding obstacles, dealing with moving goals and obstacles. Here's an example where now I have these extra functions that represent obstacles, and you can actually encode them into this, where you've now computed this reach avoid value function for how to reach your goal while avoiding obstacles. So anyway, it's a very powerful and beautiful tool. And then you kind of ride the wave back in. But the disadvantages is that the online deployment of this function is not straightforward. On one extreme, we have something that's very conservative, and on the other extreme, we have something that's too jerky, as I mentioned. The other big issue is something called the curse of dimensionality. So if you've taken any class that covers dynamic programming before, you know that when you grid up your space, if you have one dimension, then you have a single line of grid points. If you have 2 dimensions, you now have a square of grid points. 3 dimensions, you now have a cube of grid points. And this continues exponentially with every added dimension of your system. And so instead of using, a full 13-dimensional quadcopter model, you might abstract it away to something very, very simple. Or instead of having a real high fidelity model of how a human moves, you might abstract it away to humans are a double inverted pendulum, which clearly does not capture everything that humans do. And so a safety analysis over this may not be valid for the true system. So now let's talk about control barrier functions, unless there are more questions or any questions.
No hands here.
Okay. To get to control barrier functions, I'm first going to talk about control Lyapunov functions. They tend to be more well-known, at least in the controls community. So a control Lyapunov function is one that is continuously differentiable and is positive definite at all points in the domain except at 0, where it's 0. And then for all states except for the origin, there exists some control U such that the change in value over time is less than or equal to 0. This is because control Lyapunov functions are used for stabilizing systems, where this total derivative here is the change with respect to space, the gradient, and then change of your dynamics with respect to time. So if I clear a particular state and I have this value, I know that my change in value must be less than or equal to 0. So I must essentially be moving down this curve to the origin where there's an equilibrium. If we look at level sets of this control Lyapunov function, if I have a car, for example, on this particular level set, the gradient of this will be pointing outwards. And since I want to move along the negative direction of the gradient, I want this inner product to be less than or equal to 0. I'm going to look at the direction of the negative gradient. My flow field of my car, as I mentioned before, my car cannot just directly do gradient descent towards the equilibrium. It must follow its dynamics. So these are the different options of where it can go. And I want to look at the inner product between these two and ensure that it is pointed towards the equilibrium. So online, you must choose a control such that your change in value will not increase. This essentially means that you're restricted to these different futures for your car. Note that since we're saying that it only has to be less than or equal to 0, this could get stuck and not decrease. You could choose a control such that you are always moving along this level set and never actually moving closer to your goal. In order to force convergence to the goal, this is the video of that, you may want to force a stabilization rate to the goal at some desired rate. For this, we make this a little bit more strict, and we say that V dot must be less than or equal to some minus gamma V. So online, you must choose a control such that your change in value decreases enough. So you're restricting this further. Essentially, how you're doing this is if you plot V dot equals minus gamma V, this is an upper bound on what you can do. So when you have a high level of V, you must get closer and closer to the goal. As you approach the goal, it becomes a bit more lax, but you have this exponential convergence guarantee to reach the goal. If you have such a function that obeys all these properties, then online you can solve for the control that stabilizes you to the equilibrium using a quadratic program where you minimize the deviation between your desired control input and your true control input such that you obey the stabilization requirement. So when you're here, gamma is a positive number, so minus gamma is negative, and V is positive. Therefore, V dot must be less than or equal to some negative number. So you must decrease here. If you're at the origin, then V at this origin is 0. So V dot is less than or equal to 0. So this is simply including that you must not increase your value at this point. Therefore, you have stabilized to this equilibrium point and you will not leave it. So we want a function over the state space that encodes the long-term effects of the dynamics and tells us where to steer our control input in order to satisfy this stabilization property. This is generally a hard thing to find for nonlinear systems, especially if you have bounds on your input, so you can't accelerate or brake infinitely hard. And it's a big field in nonlinear control, finding valid control Lyapunov functions for various different problems, classes, and dynamic systems. Okay, what does this have to do with safety and barrier functions? Well, let's say that instead of an equilibrium, we have a control invariant set. So I'm going to lower my CLF, my control Lyapunov function down. So now it's positive outside of this control invariant set. You can think of it as like a generalization of an equilibrium point. And it's negative inside. So when my car is here, again, I have minus gamma and a positive V. And so V dot is less than or equal to some negative value. It must decrease. When my car is right here, we have minus gamma and V is 0. So V dot is less than or equal to 0. You must not increase in value. If I'm inside this set, well, now I have a negative number times a negative number. And so V dot is less than or equal to some positive value now. So you can increase the value when you're inside of this set a little bit. And if you're deep inside this set, well, then this V is going to be a stronger negative value. And so this V dot is less than or equal to some larger positive value. You can increase by a lot. So note a few things. Once you are inside the set, you enforce remaining in it, because once you reach the boundary, you are not allowed to increase your value. Note also that the further inside the set you are, the more freedom you have over what you can do. You can start moving back up, but as you move back up, over time, you will reach the boundary and then you cannot increase anymore. This is the idea of control barrier functions, just CLFs that have been lowered down. There's one small notation thing. People like to think about safety as a positive value, and so people flip this upside down. So we're going to flip it upside down and then change this to a greater than or equal to sign. But it's just an upside down control Lyapunov function. So here, v of x can be considered the level of safety now, and you want to ensure that it remains non-negative. You can solve for the online control using the same exact QP as the CLF. I have the star here because, again, we flipped the inequality sign since we flipped the function. But it's the same thing that you would use for control Lyapunov function. And control Lyapunov functions just naturally encode that when you're outside of this, you will stabilize to this set. And when you're inside of it, you are allowed to freely move around. But as you approach the boundary, you have to maintain safety. This is, again, the same curve, v dot equals minus gamma v, but now this is a lower bound. So it's a lower bound on safety now, where when you are very, very safe, you have a high value, you can decrease safety quite a bit. But as you approach zero, this exponential curve forces that you maintain a positive safety value.
You have a question?
Yeah.
Okay.
Hi, so yeah, control barrier functions have this like cool property that you kind of mentioned where like if you're in a safety critical scenario and you find yourself outside of the control barrier function, then you'll kind of go back in to the control barrier function, I guess, the control invariant set. Does reachability have some similar property like
That's
that?
such a good question. Yeah, so first off, yes, a valid control barrier function, and it's valid across the entire domain, will have that property. In practice, many papers that you see will not force this as something in the structure, and we'll get a little bit into this. But what reachability will have instead is that it'll also compute for something like this, where here's that safe set. What it naturally has instead is that each level set is control invariant. So if this is the true safe set and you've left it, so you're over here, and so your value is now negative, reachability would naturally encode that you will stay inside of this set now, but it won't guarantee that you can converge back to the original safe set. That is exactly what we're going to try to modify next. So very nice question. Any other questions?
No, looks good on our end.
Okay. So the CBF-QP nicely trades off between the performance and the safety controller through this exponential curve. So, and one thing that I used to think was a disadvantage, but now I kind of understand the advantage of it, is that it's not really trying to necessarily find the maximal safe set. You often use simpler functions that are more conservative, but also more intuitive and easy to use. So as a quick example, let's imagine that you have some dynamic system that has 2 dimensions, has position and velocity. And this is the constraint set. And so the true safe set looks something like this, or sorry, not true, maximum safe set. And so your reachability value function might be this funky looking shape defined over a grid. Someone in the CBF community might instead say, well, let's just take a subset of this maximum safe set and define this easy, maybe even analytical function in 1 dimension, just in position space. And that is clearly more conservative. You know, you can't reach the boundaries of the walls here, but it's very intuitive to think about safety just in terms of position. And if you just have this 1 analytical function, then it's very easy to query online, et cetera, et cetera. I guess this is more of a philosophy difference than a true requirement. But it does also make it easier, the design space easier for trying to construct a control barrier function. And that's very important because in general, there's not really constructive methods for this. People will try to come up with kind of hand-tuned examples like this through very similar to control Lyapunov functions, guess and check type things, or try to fit a control barrier function using data-driven type of sub-methods. You typically recover a subset of the maximal safe set. That is, in some cases, a disadvantage. So you're more conservative often. And it's typically hard to encode control bounds and disturbance bounds. That's again because you are asking so much of this function that constricting the design space even more makes it even harder to find a valid function. Okay, so just a recap between the two methods. Let's talk about how you get to the function in the first place. Oh, sorry, how you initialize it, how you get the function, and then how you use the function. So you initialize control barrier functions, again, either using hand-designed approaches or data-driven approximations. The construction is hard to do for nonlinear dynamic systems, same exact way with control Lyapunov functions. In reachability, we usually initialize with assigned distance to obstacles or the failure set. And then we do this dynamic programming. It's rigorous, but it's not scalable. Online, what we get out of reachability is that v dot is greater than or equal to 0. That was the thing that can be overly conservative. You're always running away from obstacles. Or we can do least restrictive control. That was the thing where we only intervene when you hit the boundary of safety. And so you can be conservative and or jerky. Control barrier functions use this quadratic program where you minimize control efforts such that you're greater than or equal to this minus gamma b, which is this curve here that has this nice trade-off between the performance control and the safety control as you approach the boundary. So this has fast analysis and nice trajectories. So what we did actually for that ONR YIP that Karen mentioned was ask if we can just smush these together. So can you take advantage of the good things of each approach? Can we start with all of this work that people have done for coming up with good control barrier functions for either specific case scenarios or data-driven approximations? Can we then use those to warm start our dynamic programming and just try to apply as little of this like rigorous, tedious dynamic programming as possible to get to the valid solution? And then can we use online the CBF QP for this nice trade-off between performance and safety? Okay, so that's the relationship between those. And now I'll talk a little bit about the stuff that we've done playing around with this. So first, can theory and tools from reachability be used to construct control barrier functions? Can tools for quickly approximating control barrier functions be used for efficient initialization of reachability? And then can we update these functions online based on changing assumptions and information in our environment? Okay, so let's talk about the next one. So the idea is exactly what the person was asking about. Can we encode that QP constraint into the reachability? So if you remember this, we went through this derivation where we ended up with this v dot is greater than or equal to 0. We're literally just going to add one term in that update equation so that if we go through the same exact steps, we end up with 0 is less than or equal to v dot plus that extra gamma v. In other words, v dot is greater than or equal to minus gamma v, which is just what the constraint that we want out of this. And if we do this, we literally just changed one line of code. We can construct a CVF-like function that encodes control and disturbance bounds and a maximal decay rate gamma and guarantees online feasibility for this. So here's what that looks like. So here I'm going to apply the safety controller only for reachability. I have a goal down here, I have an obstacle. This is a little 3D Dubin's car and it's pointed to the right. So the unsafe set is this region here, where if you're right here, you have to turn left or turn right in order to avoid the obstacle. And you're going to see that rotate as our car rotates. And here's what the function looks like. So here, this is what happens when you just always run away from obstacles. It doesn't even try to go to the goal, it just runs. And this is what the control signal looked like. Here, if I apply least restrictive control from reachability, this is what happens. So we're able to get to the goal, looks pretty good until you look at the control signal and you see that we had this really, really choppy thing because of the least restrictive control where we're bouncing off of the obstacle. If we instead encode the CBF QP and then apply that, then we end up with this. and we end up with a much smoother controller or control signal. Another nice thing that we can put in now is a difference between caring about infinite time safety and finite time safety. So let's imagine that you have this goal right here that you want to reach, and my Dubin's car here can't brake. And so exists no way of approaching this goal where you won't end up crashing into an obstacle. And so therefore it's not safe to reach if you want to stay safe forever. And so if you try, you see that you get pushed away. If instead you care about finite time safety, let's say you have some hybrid system where once it reaches the goal, it will switch into a different mode. And so you don't care about safety in the original space afterwards. Then you can encode this time varying aspect into the control barrier function. So you see here that the safe sets actually shrink over time because safety becomes less and less important over time. You only care about safety for a finite time and you are able to reach the goal. Okay, so yes, we can kind of minimally modify the reachability side of things to have a constructive method for generating these CBF-like functions. There is a caveat in that reachability solves for these viscosity solutions, and you can have points of non-differentiability. This is something that the reachability community doesn't really care very much about, because at the end of the day, you're doing this finite differencing anyway, but the CBF community does, the CBF theory community does care about. And so therefore we call these control barrier value functions to make sure that we're not claiming that they are differentiable everywhere the way that the CBF community wants it to be. But we have, anyway, I won't get into the details there. Next, can we use tools from data-driven approximations of control barrier functions and then minimally modify them in order to get not just approximations, but valid control barrier functions? So here's an example from my good friend and colleague, Professor Sean Gao here in computer science, where he had this race car game and they trained this neural CBF. And so you see it's positive here and negative here. So you see the zero level set. And if you look at the slice of the zero level set and roll out a bunch of trajectories, the ones in green are the ones that stayed safe, and the ones in orange are the ones that did not stay safe. So what you can do if you're training a neural CBF is find all these points where you are unsafe, use those as counterexamples, and then do counterexample guided training and try to refit your function. The problem is the more and more that you try to refit your function, you may be introducing new areas where you have leakages in your zero level set. And so we even found when we were applying his code, and he works with Choo Fan, so we were using both their code bases, it's really hard to train a neural control barrier function that's actually valid, that actually will keep all your trajectories safe. They may do pretty well on average, but if you care about safety, you care about something stronger than on average. And so we are asking, can we take these data-driven approximations and refine them? So here's an example of one that we used that was conservative in some cases. Here you see that we're not able to quite reach this point, and it's unsafe in other cases. So here, when we apply the safety filter, we end up going through this obstacle here, the floor, and then overshooting. And the question is, can we refine this function in order to get a good safety filter that is not overly conservative, but also is safe? And we found that if we initialize with that data-driven control barrier function or hand-designed control barrier function that assumes no control bounds or something like this, then every iteration of our dynamic programming will take something that's too conservative and is guaranteed to not make it more conservative, and in practice typically makes it less conservative. If we take something that's unsafe, then every iteration will increase safety, and upon convergence, you are guaranteed to have safety. So here's like a little visualization example. So here we started with this overly conservative control barrier function. In red is the obstacle, and in green is the true maximal safe set. And you see that as we iterate, we're actually able to reach that true maximal safe set. And you can see that our new safety filter is able to not go through the floor and is also more performant than the previous one. And what's nice on our end, on the reachability end, is that convergence is much faster. This is because you're initializing with something that is pretty close to the true solution, hopefully. Fingers crossed, there's no guarantees on that, right? If you give a really bad guess, then it might be worse. But each iteration of our dynamic programming is still over a global grid of the state space. And we were asking, is that really necessary? So you see that maybe it's not all that important to update your function over here. Maybe you can restrict what you're updating to these regions that are not certified. And so that was our next step. We took the neural control barrier functions from Sean's group. Sean's a formal methods guy, and so he was able to also provide us with the regions that they were not able to formally certify are valid. And we initialized in those regions, and we have an algorithm to determine what is the region within which we need to actively update the value function. And so you see in gray are all the regions that they could not certify of the neural control barrier function. And here in blue, you see us updating those. And you see the boundary of the original safe set and then the boundary of our safe set. And note that we can either just find the barrier function associated with the trained neural control policy. So if you're just trying to ask under this neural control policy, what is safe and what is not safe, we can just directly apply that neural control policy and tell you. Or we can actually update the control policy along the boundary to find the control barrier function with the largest safe subset of the initial safe approximation. So here's rolling out trajectories of the original neural CBF. You see again in green and then in red. I promise that we did try very hard to train this well. It just is really hard to fit these for nonlinear systems with bounds on control and disturbance. And then here's what ours looks up like after a few rounds of patching. Note that we don't have 100% of safety. We think this has to do largely with the fact that we're discretizing still over a grid. And so we're trying to do a continuous analysis over a discrete grid. So we're doing some follow-up work on like how finely do you really have to sample in order to be able to capture all of these loose trajectories here. But if you look at comparisons here, if I applied the neural nominal policy, so the policy that was used to train the neural control barrier function, then both methods do pretty well. Ours does better, but both methods do pretty well, and they have less than 5% unsafe trajectories. However, if you use the neural control barrier function with a different performance control policy, so something that's different than the one that it was trained on, even just LQR, then the percent of trajectory rollouts that are unsafe, it was over half of them that were unsafe compared to ours. So the point was that local patching is approximately 2 orders of magnitude faster than our original refined CBF work. And we're able to get better control barrier functions than we can using the data-driven approaches. So this and my student's going to be presenting at CDC this winter. Okay, and then lastly, can we update these functions online based on changing assumptions and information?
So, Sylvia, we have a question.
Oh, sorry, I should have stopped.
No,
Yes.
no worries.
Going back to you mentioned like discretization causing like
I didn't quite hear. I heard go back, but I don't know
Right,
what go back to.
the having some unsafe trajectories still because of like discretization, you
Yeah.
think? Is that a phenomenon that occurs also just like for vanilla reachability? Like
Yes,
like, is that
it absolutely does occur for vanilla reachability.
Okay.
Yep. And in general, there hasn't been like the fluids community has really figured out, adaptive gridding and all this kind of stuff of how to make sure that you're really truly capturing the PDE as it's evolving. The reachability community hasn't really. You kind of just add a bunch of grid points and hope for the best. And there hasn't been a good, I think, thorough deep dive. At least, I'm sorry, I shouldn't say hasn't. I have not seen a good thorough deep dive on how finely you need to discretize your grid given your system dynamics and problem formulation. And I think it would be really interesting if for people who are familiar with like the meshing and adaptive gridding and whatnot in the fluids community to think about how we can apply similar types of tools on our side of things. But yes, we after doing this, we had the same question and we started rolling out trajectories for just like normal reachability problems and saw that we have a similar type of thing, where in theory, you guarantee safety, but in practice, when you discretize, it depends a lot on how finely you're discretizing.
Yeah, we have another hand up.
How does this work compare to the work that like tries to learn the value function of, and then use that as a CDF directly, like of the nominal policy or something like that?
Isn't that what I just, maybe I'm not understanding what you're asking about for comparison. What do you mean by learning the value function?
Maybe I'm misunderstanding. Yeah.
I think so.
Karen, did you understand?
Yeah, I think that I think there was just some confusion, but I think what's happening here is we're learning a CBF or a value function. It doesn't have to be a CBF, but in this work it was a CBF from data, and then fixing it up through kind of this.
Oh, is the question like, could you do the same thing with deep reach?
Or
Like,
like,
could
does
you-
does it have to be a CBF, or can it just be a generic value function that's not necessarily a CBF?
Yeah, I think you could do the local patching for reachability. Somel and Andrea did something kind of, Somel Bonsall and Andrea Baichi at Stanford and CMU respectively did like a local updating of reachability based value functions. They weren't doing it for neural value functions, but they were doing it for if you are navigating through a space and you see that like a local thing has changed, how do you locally update your value function? I think that work could be easily applied to things like deep reach where you're learning the value function. The main challenge is that you're still at the end of the day doing some discretization along that boundary. You're removing a lot of the discretization that's required, but it's still going to struggle with really high dimensional systems. In terms of learning neural value functions, we have some work that we're hoping to submit to L4DC, in which if we use this tool from the applied math community called hop reachability, which works for linear time varying systems, and we use that to help guide the training for reachability based value functions, we can do much better than just trying to do the training on its own. But that's a whole different talk that I'd be happy to get into if people are interested. I'm very excited about it right now, but it's not this talk. Any other questions related to this?
I don't have a question, but just maybe a comment going back to kind of this adaptive grid size kind of question. Something I tried a few years ago was actually passing through, doing a change of variables in the dynamics, so that you do, through this change of variable, you do get a varying grid size, right? If you pass your variables through like a quadratic, then you have close to the origin, the grid points seem to get closer together versus as you kind of go out, it gets more sparse. I tried it out. I don't remember what happened. Like, I think it just made it run a little, I forgot what I was running it on, but I remember some things being a little slower because you had to pass it through more operations.
Right, and I guess it would change how stiff your dynamics are, and that, but there's always going to be a trade-off there.
Yeah.
So
So
that's
yeah, I didn't do like a deep dive analysis, but I just remember trying out like
Yeah,
if
cool.
like certain variables are like, oh, I care more about what's happening close to the origin, and I still want to cover things far away from the origin, but less importantly, well, I want my grid to be more sparse. I just, pass it through a quadratic or any other transformation that makes sense. So maybe
And I know people like Thomas Liu, right, in Marco's group, they're doing the sampling based reachability stuff, are thinking about some things related to this for when you're doing sampling based approaches. And
yeah,
I
like
think,
how do you maybe like bias your sampling to
Right,
get a more
right.
informative or more accurate?
or like in the neural CBF work, they always bias their sampling to like around the boundary of the safe set, because like we were saying, oh, this goes back to one of the earlier questions. you really want to make sure the boundary of your safe set is pretty good. And so often the learning-based approaches really focus there, and they focus less on things like making sure that you have this nice convergence when you're outside of the safe set. So they really want to make sure that the QP is feasible along the boundary. They care a little bit less about if the QP is feasible inside or outside of the boundary. If that makes sense. And so often these CBF approximations are not, first off, often not valid on the boundary, but second off, extrally not valid outside of the boundary on either end.
Gotcha. Cool, thanks. Are there any other questions? Okay, cool. Yeah, go on.
Okay, and then can we update these functions online based on changing assumptions and information? So now we're actually trying to see, like, can we put this in the loop? So here are some experiments that my students finally thrown together, and we're trying to force him to get himself through a journal submission for this. Here we have an environment where we have these obstacles and a goal, and in green is the boundary of the safe set. And here it's going to not properly update its safety analysis with respect to this unseen obstacle. So you see as it moves through and it senses this obstacle here, if you look at what's going on down here, it crashes. Oh, wow. If instead we do our refining, so when we see this new region, we update our safe set. Let's look at what happens down here first. So I'm grayed out up here, so we don't focus on that. And let's see what happens here. One thing I want to emphasize is see how the green barrier is kind of changing. That's because the safe set's defined not just in position space. Remember that now we're talking about the maximal safe set, so it's defined in multiple dimensions, and I'm just visualizing it. So as it moves faster, you will see that the boundary of the safe set moves away from the obstacle. When you're moving faster, you can't get as close to the obstacle without crashing. So, okay, let's see what it's doing. So when it senses, oh no, that's the bad one. Okay, let's see what happens when it senses it. So it senses it, and you see that the green set will start moving until we update it and we're able to move safely around it. And if you look at what's happening then in real life, see, sure enough, we're able to move around the obstacle. If we have some wind as another example. Oh, go ahead.
So just a quick question. In that video, did the drone kind of like slow down a little bit when it saw the obstacle? Because it,
Yeah, the safe set became more conservative. And then
okay, was it slowing down because of the safe set, or was it slowing down because it was like trying to compute it and it needed some time to get a better?
I don't know if my student put in like any sort of weight override, or if it just naturally slows down because it becomes more conservative. I don't know the answer to that, but I will find out.
Okay, because it'll be interesting to like if it's like some kind of perception cone, and then it sees something, but then wants to get more kind of information and more confidence on this new unseen obstacle before moving on. That could be kind of,
yeah, the one that I showed just now doesn't guarantee safety when you see the new obstacles. This one you'll see does for a static environment, in that you always start with something more conservative. So instead of initializing with the entire region assumed known, it initializes with just what you can locally sense is safe and slowly updates this. And so it would see exactly the type of behavior that you were talking about, where it hesitates until it can keep moving forward. Oops. And so we're going to select waypoints that are as far to the goal as possible, but still inside the current safe set. So you see the waypoints being selected as the safe set keeps growing and growing. And then here, when it detects this wind, it has to update its safe set. So it's actually updating this safe set based on the sensed wind and the new disturbance bound. And then down here, once it no longer detects the wind, it changes the disturbance bound back to the default, continues to update its safe set, continues to inch along to the goal, because here we're prioritizing being safe and conservative until we can eventually select the goal as the waypoint. And so all this is happening in real time. This hasn't been sped up at all. Then I have some undergrads who are working on doing this on a jackal. So we have, this obstacle here. You see the safe set expanding, and then they throw a rock at the obstacle to create an avalanche here. It has to update its safe set and move around. The reason why I'm having them practice this on a ground robot is because we want to merge this with some other work we're doing with Nikolai Atanasov and Jorge Cortez, where we're doing dealing with now robustness to measurement errors. So if you're using this LiDAR here, and so you're only getting a sample from pings, LiDAR pings of your obstacles around you, how do you design the robustness to potential measurement errors and incorporate that into the structure of your CBF? Currently, the work with them is assuming that you have this infinite acceleration or braking type of thing. So your CBF is essentially a signed distance function, but they want to merge it with our work to make it more robust in general. And then Henrik Christensen and Sean Gao were starting to put CBFs on different ground robot platforms. We're starting with this Japanese company that wants their robots to stop hitting their employees. It's a warehouse company. And so they're asking us to test out some of these CBFs. And then Henrik said that he might want to try putting it on his golf carts, which would be fun. Okay, with that, it's 10:55. So let me skip. I was gonna do some bonus stuff, but I think in the interest of time, let me skip ahead to this part. Okay, so I didn't do any of this work. This was all the students at the end of the day. Largely my student Sander Tonkins here. And so thanks to him, he also has a bunch of undergrads who are working on the robotic experiments. So thanks to them as well. And then with that, I will end. We have a lot of other projects I didn't talk about. Here's just a little sampling of some of them. Thank you very much.
Thank you. Yeah, do we have any questions in the room? Was that a hand? I had a quick question. Going back to that patching work where you had some neural CBF or some initial, I guess, initialization. Can you give a bit more, can you share some kind of more details about how this patching is happening?
Yeah, sure. So it's literally creating grids in the regions that we cannot certify. And then in those regions, you have to determine which states you need to update. And so we initialize, you can either initialize with literally all the states, or you can initialize with the ones that my colleague Sean cannot certify. So he, using D-real stuff, can certify that some states along the boundary are guaranteed to obey the CBFQP condition and some states are not. We grid up in that region where they are not certified, and you essentially, based on some Lipschitz assumptions, have to expand that region by a certain amount. And as you update the value function, if you find that the value has changed, then you locally expand even further the states that you're considering. If you find that the value has not changed, then you can remove that state from your active set of ones that you have to update. This is the very, very high level idea of how we choose which cells need to be active and which ones are not. And then if you have discretized correctly, key part of it, then you have some guarantees on this process managing to recover all the safe states within that region. So the details of all of that is in the CDC paper. Weirdly, the main issue that we're finding is that this requires a lot of like meta level processing, right? Of like kind of deciding, you have this algorithm to decide which states should be active, and then you have your dynamic programming. For the refined CBF, where we just update everything everywhere, It's actually pretty straightforward to do GPU acceleration on that because you don't have to change what grid points that you're reasoning over. You just update everything and you can do it in a very like parallel type of way. And so in practice, at least for medium dimensional systems that we're looking at, so like 5D, 6D, the refined CBF, if you use GPUs, can be more computationally efficient at the end of the day than the patch one, even though you're doing way more Hamiltonians.
Gotcha.
Yeah, so I was not expecting.
Yeah.
But it's kind of nice that just the like straightforward vanilla thing might be easier to use at the end of the day anyway.
Yeah. So it sounds like the kind of patching, like, you have to do some kind of sequential kind of processing, and that's why.
Yeah, there's a lot of reasoning over what are the regions that you do in fact have to patch. Whereas if you just blindly patch everything, then there's less reasoning that needs to happen.
Hmm.
Yeah. Other questions?
Lots of people have thinking faces, so.
Uh-huh.
Oh, we have
Okay,
one.
well, you're welcome to learn more about our work. Karen tells me that my website's been updated. Hopefully that means the students who's in charge of the website has been doing her job. Or my email is sherbert or sherbert@ucsd.edu. So you're also welcome to reach out to me that way.
I think we just had one last question.
For the drone, like adaptively expanding the safe set video at the end, those waypoints, were those like manually specified or is it automatically selecting them?
It was automatically selecting them. The process was find a very, very, very naive, dumb selecting process. Find the point that is closest in Euclidean space to the goal, but within the safe set. You could use something smarter if you wanted to, but this worked fine for this.
Cool. So it's right at 11. So thank you so much, Sylvia, for your time and presentations. I'm inspired by your research and kind of some of the visualization in explaining reachability and CBS.
Thank you.
Thanks again. So everyone, round of applause.
Okay.
Okay, cool. Thank you so much, and I'm sure we'll catch
All
up.
right. See ya.
Okay, bye. Okay, so I'm gonna